All right, so let's talk about how to fit a line to bivariate data. All right, so just as a little bit of review here, remember that the whole purpose for dealing with bivariate data and statistics is to try to use one variable to help predict the value of the second value. So we have x as our explanatory value. This is the one that we're trying to use to make predictions with. So we want to know what happens if we alter the weight of a vehicle, for example. What is that going to do about the miles per gallon, about the gas mileage that receives. So our explanatory variable is the x-axis and our response variable is the y-axis. And so we're trying to manipulate or examine values of the x value to try to make predictions about what we think is going to happen on the y value. And what we hope happens is that there's a linear pattern, because if there's a linear pattern, we can make a nice line through the data. Sometimes you don't have a linear pattern. Like this is a very strong curve right here. This looks like an exponential. And so this would be a strong nonlinear relationship. But what if it was linear? What could we do? Okay, so dealing with this gives us this least squares regression line. Okay, so in statistics, the equation of our least squares regression line, of the line that fits the data the best that we can possibly do, is y hat equals a plus bx. Now you'll notice that this is not y equals mx plus b, our friend from algebra. So you're going to have to just get over that one. The slope m is actually b. B is the slope. Okay, and the y-intercept, which you used to call b, is actually a now. So a is the y-intercept. So it starts with the y-intercept and then it increases or decreases by that value of slope. So we're not using this mx plus b formula. Part of the reason why is just in statistics, it builds one term at a time. So a quadratic would look like a plus bx plus cx squared, and then we would have plus dx cubed plus etc. as it goes on. So instead of constantly shuffling those variables and putting them in different places, this is what we're dealing with. So a plus bx, a plus bx, and this y hat is the predicted value of our response variable, because most of the time that line of best fit is not going to fit exactly through our data perfectly. Instead, we're going to have this predicted value of y that goes through. All right, so again, a is our y-intercept. This is the value of the response variable when x equals 0, and sometimes this is not going to make sense in context. And so you'll just have to kind of always think about that. If I'm trying to interpret what this means, does it actually make any sense? And then the slope of the line is the rate of change. And basically what we're going to do is you're going to have this interpretation. If you're asked to interpret the slope, you're going to say as x increases by 1 unit, the y value tends to increase or decrease by b units. Okay, so the predicted value of y is going to either increase or decrease by a certain amount of units, tends to predicted value as x increases by 1. Okay, so we're going to try to interpret those in a minute. Now, the way this is calculated, so in Algebra 2, you probably would have just arbitrarily picked 2 points that look like they fit the data. You would have found the slope through those 2 points and then used that y minus y1 equals m times x minus x1 to find that equation. In statistics, we don't do that. Instead, what we do is we take our little line here, and you can see the little guy in the corner, and he kind of like moves it around. Okay, so there's like this little guy inside your calculator doing this. And what we're trying to do is we're trying to minimize the distances between the actual data values and the line itself. Okay, so what is the minimal distance right there? So we want the sum of the squares of those numbers to be as small as possible. So the line that has that data as small as possible, that is the least squares regression line, which is abbreviated LSRL. Okay, now these little differences right here, these little d's, these are called residuals, and we're going to talk about those again in section 5.3. The residual value is the actual difference between what we observed the y value to be versus what we predicted the y value to be. And the reason again that we're interested in y is that's the whole purpose of this thing to begin with, is to try to use the x value that we are manipulating or changing or observing to try to predict what's going to happen in that y value. So these are my residuals, and I want those to be as small as possible. All right, so the formulas on your formula sheet are provided to you. So you have your y, I thought I was highlighting, not marking out. Okay, so y hat equals a plus bx, and there is an equation on your formula sheet for b and an equation on your formula sheet for a, so you could calculate those by hand if needed. Notice that we have the r, which we have a formula for, and the standard deviation of x and the standard deviation of y. We also have y bar, which is the average y value, and x bar, which is the average x value, which you could also calculate. I don't think you're probably going to need these. We will almost always use our calculator for these sort of computations. However, if you ever find yourself in a problem and you think, I feel like I should know how to do this, but I don't feel like I have enough information, take a spot check at these formulas, because there might be a case where they may have given you 3 of the 4 things that you need, and you really just have to solve an algebraic equation. Okay, so just kind of keep those in the back of your brain. Now, just as a general note, the least squares regression line always passes through the point x bar, y bar. The point x bar, y bar always occurs. So the average x value and average y value, that is a point on the least squares regression line, always, every single time. Okay, all right, so here is an example. It says the number of calories in a food item depends upon many factors, including the amount of fat in the item. The data below show the amount of fat in grams and the number of calories in 7 beef sandwiches from McDonald's. And it says what's the explanatory variable and what's the response variable. Okay, so it says the number of calories depends on many factors, including the amount of fat. So that means the calories are our dependent variable and the fat is our independent variable. So the independent variable goes on the x-axis and the dependent variable is the response to that. So we know as fat goes up, it's probably the calories goes up, and as fat goes down, calories also goes down. So the number of calories is dependent on that fat. So my explanatory variable, which we're going to use as x, is the fat content, and our response variable, that's y, that is our calories in there. It says construct a scatter plot in your calculator. Does the relationship appear to be linear? So notice that this says construct a scatter plot, and just for your notes, I'm not having you draw it out. But if on the homework it asks you to construct a scatter plot, you are expected to actually sketch the scatter plot. Okay? All right, so you're going to actually draw it in there. If it says make a scatter plot, don't just say, I did it in my calculator. You got to do it on your paper as well. Now, I have jumped ahead and I already have these values entered. And notice that I have named them using X is fat and Y is calories. And I highly recommend that you do that. That's very helpful later when you're trying to pick the right one for which axis. Okay, so I've already entered my data into a list and spreadsheet. And I'm going to add a new page, which is a data and statistics page. I'm going to drop the fat on the x-axis and the calories on the y-axis. Does this look linear? Yeah, a lot. I mean, this is great. Now, it's not perfect, but that is a very strong, positive, linear relationship. All right, so does this appear to be linear? It sure does. Yes, very strong, positive, linear relationship looks like. So find the correlation coefficient. Now, anytime you see that correlation coefficient, you're going to think R, okay? And then it says find the equation of the least squares regression line, interpret in context, interpret the slope. All right, so what we need to do here is we are going to run some analysis on this. And there is another video that you should have already watched to show you how to do these keystrokes. So I've got the data entered. I'm going to go back to my page with the data, and I'm going to, I know I need R, and I can find R in the 2 variable statistics calculations, or I can find R in the regression analysis. And since I looked forward and I saw I also need the regression analysis, I also need the A plus BX, I'm going to run that one instead. All right, so with this data in mind, I'm going to press Menu, Statistics, Stat Calculations, and then I want number 4, which is the linear regression for statistics, the one that says A plus BX. A plus BX, not MX plus B, that's for algebra. A plus BX, it's going to say, what's your X? It is fat. What's your Y? It is calories. Okay, I'm going to click OK. And I get that A is, so the regression equation, A plus BX, A is 110.44. B is 15.1682, it says R squared, which we're going to talk about in section 5.3, is 0.9956, and R is 0.9978. And then also you see these residual values. So those are the differences. So what it's saying is for every single one of these points, here is the actual difference. The first point was 0.3 below the line. The second was 15 above the line, etc. So you actually can see the actual residuals in that little command here. But these are the three numbers I want, A, B, and R. Okay, so I have these copied into my notes. R is 0.998. Okay, so I'm going to interpret this. So 0.998, that's strong, because if it's above 0.8, it's strong. So there is a strong, and it's positive linear relationship. And then I want to say between X and Y, but I want to do it in context. So I don't really care about X and Y. What I care about is fat and calories. There is a strong positive linear relationship between fat and calories. And this says find the equation of the least squares regression line, interpret in context. So I pulled off my calculator that A was 110.4, B was about 15.2, and I know that y hat equals A plus bx. So I'm just going to write it out plain the first time. So y hat, don't forget the little hat because that means predicted y, is A 110.4 plus bx 15.2 times x. There is my least squares regression line. Now, this is the only time when you see this interpret in context that you are not going to write a complete sentence. Okay, almost from every other time, if it says interpret in context, you're going to write a complete sentence to explain. There's a strong positive linear relationship between X and Y. You know, you're going to write this complete sentence. Here, you're not going to. All you want to do is you want to change these so that you're using the actual words. So instead of predicted Y, we're going to write predicted calories. So I'm going to write the word calories. And then you can either put a hat over top of it for predicted, or you can actually write the word predicted calories instead, equals 110.4 plus 15.2, and this time you're going to say times fat. Okay, or you could say times grams because it's in grams. Okay, so interpret in context means just write it with real words instead. We're going to take 110.4 plus 15.2 times the grams of fat. That's going to predict the number of calories we need. Then it says interpret the slope of the least squares regression line. Now remember, the slope is the one that goes with the slope is the one that goes with X. So our slope is the 15.2. All right, so think about what this is saying. It's a positive slope. So you think rise over run. The Y value is going up by 15.2 over 1 for the X. So we're going to say that in so many words. We're going to try to write this prediction. So we're going to say the predicted value of, now what was Y again? You got to think, you know, that's calories. Okay. And then I'm going to use this phrase tends to increase, because it's positive, by 15.2 calories for every 1 gram increase in fat. The predicted value of calories, the Y value, rise over run, predicted calories, tends to, doesn't do it every single time, it just, we're predicting that it will, tends to go up by 15.2 for every 1 value of X. In this case, that's over 1 gram increase in fat. Okay. And it says, what would you predict for a beef sandwich that had 30 grams of fat? All right, so 30 grams of fat. So I'm going to sit here and I'm going to plug this in. So always show substitution into your equation. So we're predicting calories. So that's the Y hat part, equals 110.4 plus 15.2 times 30. All right, and that comes up to, let's see, I punched that in my calculator, about 566.4. Now, I'm going to answer this question over here. I'm going to say that's 566.4 calories. What amount of calories does it predict? Here we go. Okay. And then I've got what amount of fat would you predict for a beef sandwich that had 500 calories? So again, the fat would be the X. So I'm going to say 500 calories equals 110.4 plus 15.2 times X. Okay, so I'm going to solve for the X this time. And if I subtract 110 and divide by 15.2, I get that X is 25.6. Okay, so I'm going to answer my question, 25.6 grams. That's how much fat this would predict. Okay, now note for the predictions here. The purpose of a least squares regression line is to predict Y. Predicted value of Y. It's not to predict the X. So while you can use the equation this way, this is not the purpose of this equation. This is not a proper use of this equation. If you really want to be predicting the X value, you need to flip-flop your data. Okay, and make a new equation line. But this is really for predicting Y, not for predicting X. Okay, all right, so next question. So studies have shown that people who suffer sudden cardiac arrest often have a better chance of survival if a defibrillator shock is administered very soon after cardiac arrest. The accompanying data give Y is the survival rate in percent and X equals the mean call to shock time in minutes for a cardiac rehabilitation center and for 4 communities of different sizes. All right, so here's what this data, so I look at this and I see like this first point here, 2 and 90. So this is saying that the mean call to shock time, on average, when we looked at this particular facility, it takes them about 2 minutes on average, a typical amount of time between the time a person goes into cardiac arrest and they receive a defibrillator shock is approximately 2 minutes. That's a typical time that happens. And their survival rate is 90%. So of all the people who receive this defibrillator shock, 90% of them survive. Okay. All right. So it says construct a scatter plot in your calculator. Does the relationship appear linear? Now, again, if you're asked to do this on the notes, I want to see the scatter plot in there. So I'm going to pause and I'm going to go enter this data into a list and spreadsheet. Okay, I'm back. So I took my calculator and I let X, which is the mean call to shock time, and I let Y be the survival rate, and I entered my data to 90, etc. Okay, and I'm going to, it said, does it appear linear? So I'm going to construct a scatter plot. I'm going to go new page, data and statistics page. Here we go. And I'm going to drop my X mean call to shock time on the X axis, and I'm going to put my survival rate on the Y axis. Now, does this look linear? Maybe. I do not like this point right here at 9.5. I sure wish that wasn't there. But if we were going to say possibly linear, maybe it's curved. All right. So, I think we could probably say it does appear to be decreasing, at a fairly constant rate. Maybe it's leveling off. Not really sure what's going on there. So up until that last point, it looks fairly linear. So let's kind of stick with that. And it looks negative, looks fairly strong. So I'm going to go back to my notes here for a second. Oh, I've got all kinds of notes up. Here we go. Does the relationship appear linear? Yes, for the most part. Okay. It says find the correlation coefficient, and then down here it says the least squares regression line. So again, I'm going to run through this data. I'm going to go back and I'm going to press menu and statistics, stat calculations, and remember I want number 4, which is the least squares regression line for statistics. So number 4, A plus BX. And it's going to say what's X and what's Y. Okay, agree. And I get A is 101.3, and I get B is negative 9.26. And remember, B is the slope for statistics, so that makes sense. It's a negative because it looks negative. I've got my R squared right here, and then R is negative 0.960. And just while we've got this calculator up, I'm going to go over here and I'm going to look and see what does that line look like. So remember from the previous video, I could go analyze the regression. Oh, what have I just done? Haha! I want to analyze the regression, and I'm going to hide that quartic equation that it thinks it is. And, oh, I did it again. This is why we can't have nice things. Show the linear. There we go. So this is the line that goes through. Hide that that other one that's happening there. hide the power equation. All right, so here is what the line, that least squares regression line, would look like as it goes through there. All right, forgive my poor calculator skills. Here we go. All right, so I'm going to go back. It says find the correlation coefficient. That's R. So we read that off the list. Negative 0.960. So it says interpret. So I'm going to say there is, now this is a negative, okay, but it is absolute value is greater than 8.8. So we're going to say there is a strong negative linear relationship between, and I'm going to write mean call to shock time and survival rate. Okay, there's a strong negative linear relationship. That's what that R interprets to. It says find the equation of the least squares regression line. All right, so I have my A and my B from the calculator. So A plus BX, that's Y hat. The predicted Y is 101.3 plus BX. I'm actually going to say minus because it's minus 9.3x. Here is my least squares regression line. Interpret in context just means I'm going to rewrite the thing with words instead of with variables. So the Y would be survival rate. So I'm going to say survival rate. And you can actually use the word predicted, or you can put a little hat over it. That's fine. Equals 101.3 minus 9.3. And I need to write mean call to shock time in this space, but that's really a lot of words. So I'm just going to go up and I'm going to grab the unit here, which was minutes. Okay, mean call to shock time in minutes. Okay, so there's my context. It says interpret the y-intercept and the slope of the least squares regression line in context. Okay, so I'm going to go ahead and here is my y-intercept. Remember, the A is the y-intercept here. And the y-intercept is the value of y when x equals 0. So let's think about that in context. When x equals 0, so when, what was x again? X was minutes. Okay, when mean call to shock time is 0 minutes, when x equals 0, the predicted, oh, what important, predicted, that's such an important word, because not the actual survival rate, the predicted, what does the line say is going to happen? The predicted survival rate is 101.3%. All right, folks, I got a problem with that. So if I just go around, so 0 minutes since cardiac arrest. So if I shock someone at the moment of cardiac arrest, I am actually going to not only increase the survival, they're going to survive, but also I'm going to bring somebody back alive in the next room because the survival rate is 101.3%. This doesn't make any sense in context. I can't have a survival rate greater than 101.3%. Okay, so I'm just going to say that this does not make sense in context. Okay, so that doesn't make sense. Like, yeah, that's what it means, but we can't have a survival rate of 101.3. That's ridiculous. Okay, so if you ever come up with a problem and it doesn't make sense, don't feel like you have to pick something that doesn't make sense. Okay, like, oh, the weight will be negative 153 pounds. Like, that doesn't make sense. So none of the above. Okay, now what about the slope? So my slope is the B value. It's negative. So what that's saying is rise over run. It's falling. The Y value is falling by 9.3 for every 1 increase in X. So the predicted, oh, and that's such an important word, predicted, what is Y? What is Y doing? That is survival rate. The predicted survival rate decreases, because it's negative, by 9.3% for every 1 minute increase in mean call to shock time. And I'm going to change this just a little bit. I'm going to say tends to decrease. That's a little bit weaselier. The predicted survival rate tends to decrease by about 9.3% for every 1 minute increase in that mean call to shock time. predicted y value is decreasing for every 1 minute increase in that time. It says predict the survival rate in a community with a mean call to shock time of 10 minutes. All right, so this is a plug and chug. I'm going to show that survival rate, that y hat. Okay, I'm going to go 101.3 minus 9.3, and I'm going to plug in my 10 minutes here, and that comes to 8.3. So 8.3% is that prediction. Okay. Now, one thing that you're probably going to have to do on the AP test is interpret computer printouts. In the real world, we're probably not using a TI-Nspire calculator. And also on the AP test, they're probably not going to give you a massive pile of data that they want you to enter and deal with. And real life tends with large sets of data, not small sets of data. So most of the time, what we're going to do is we're going to feed something into some sort of data analysis program. And one of those would be Minitab. There are also several other programs out there, but you do need to know how to read this. So I have this regression analysis, weight versus height, and this one actually gives you the regression equation. Weight equals 851 minus 10.8 height. A lot of times you don't have this part though. You only have the bottom part, and this has all kinds of business on here. So notice it says predictor, coefficient, SE coefficient, T and P, constant, height, S equals, R squared equals, R squared adjusted equals, there's all kinds of stuff on here. All right, so what is the explanatory variable? So when you go to read this, here is what you basically want to look at. You want to find this thing that says coefficient, okay? This coefficient column should have two numbers in it. The first number is the A and the second number is the B for your equation. Okay, so A plus BX. Okay, these are the coefficients. So A is the constant term. A is the constant term. That's the one that doesn't have an X, A plus. And B is the coefficient on height. And that's going to be our BX. So there is our explanatory variable, height. Says, what is the slope of the least squares regression line? Okay, so remember, y equals a plus bx. The number with x is the rate of change. So the slope, b, is negative 10.846. And so remember what that means is that it appears, so looks like weight is y. Predicted weight tends to drop by about 10.8, whatever this unit is, pounds, for every 1 unit increase in height. All right, what is the y-intercept of the least squares regression line? That would be A equals 850.6, or you could plot that as an ordered pair. That would be 0, 850.6. Okay, so that's saying that when x equals 0 at a height of 0, the weight of whatever this is 850.6, whatever unit weight it was. What is the correlation coefficient? All right, so remember, correlation coefficient is R. Oh, wow, I have that pen selected to be very wide. So the correlation coefficient is R, and we don't have R, but we do have R squared. So notice there's an R squared there. And just as a reminder, on your TI-Nspire, you're also getting R squared as this value. Okay, so you have R squared and you get R. Okay, so R squared is on there. So R squared, so what does this mean? R squared is 90.3%. So if R squared is 0.903, we should be able to find R by taking the square root. 903. I'm going to put that in my calculator. The square root of 0.903 is 0.950, but there is a catch. Okay, remember that R also tells you the direction. So if your data values tend to be sloping up, we have a positive R. If your data values tend to be sloping down, we have a negative R. And when you take a square root, technically you've got that plus or minus out in front from algebra, remember that? So is this positive or negative? What you want to do is it always matches the slope. So we know that if the slope is negative 10, that our R value is also going to be negative. So this one's going to be negative because it needs to match the slope. If your slope is negative, your R value will be negative. If your slope is positive, your R value will be positive. So if you can't see the scatter plot, you have to be able to use the slope from that regression analysis. All right. Now, one last final thought. A couple things. The regression analysis is always going to give you, like if you do the two variable statistics, you'll get mean X and mean Y. That is always a point on the least squares regression line. So if you were trying to graph that and you know what the average X and know what the average Y are, you can always graph the least squares regression line using that and some other point you can find through substitution. In general, unless you're asked to do so, you really shouldn't be predicting X with these. Like if they say predict X, you go ahead and do that, but these are for predicting Y. Y is our predicted value that we're dealing with here. This is the appropriate way to use this line. And then you also need to be really careful about predicting for Y values that are outside your range of known X values. This is called extrapolation. And once again, I've crossed out instead of highlighted. Let me see if I can fix that. All right, so these are outside your range of known X values. This is called extrapolation. So here's the problem. Okay, so I've got this data, and let's imagine what we see is in the sample. We see this little section. So from like, 17 up to 37 or something like that. We've got this sample and we go, wow, look at this. This has a strong positive linear relationship. We write this least squares regression line equation. It's beautiful. It fits the data. We've got this nice straight positive line. That's what we see, and that's what we think is happening. And as a result, if we wanted to make predictions, I've got I want to make a prediction for, what about when it's 30? What's it going to be for 30? And I look up, you can see there's an actual value of 30 here, and here's a predicted value of 30. That's not too bad. I'm doing a pretty good job of predicting that. So my predicted value and my actual observed values, not a whole lot of difference. But if I wanted to predict, say, 50, okay, and I go up and 50, here's the actual observed values around 50. I am not hitting that at all with the least squares regression line. That is way off. And it's because outside my known data, I can't tell that behavior is actually changing. So even if you see a really strong positive in what you can see, you need to understand that outside of that boundary for X's, not good for predictions. So extrapolation, that would be making predictions outside your smallest X. So in this case, like smaller than 17 or larger than like 37. If you're using extrapolation, you're trying to predict outside, that gives you unreliable results. Okay, so unreliable results. Interpolation, right here in between these two values, you're good to make predictions. Use the least squares regression line for predictions on that all day long, no problem. Okay, but outside, not a good idea. And that's the reason why a lot of times our y-intercept doesn't make any sense, because if your first data point is positive 50, then using that y-intercept, it's kind of like extrapolating. It's predicting what's going to happen when X equals 0, and that's outside your known data values. So just kind of be careful. Okay, so a lot of times you're asked, how would you feel about, predict what happens when X equals 50? And then you answer it and it says, how confident do you feel in your results? In this case, I would not feel very confident. And I would say, I am not confident in results. 50 is larger than my largest X value, which means that making a prediction is extrapolation, which means my results are unreliable at best. Okay. All right. Thank you very much.